Hey guys, Miss Marusik here, and in this video we're going to talk about calculating enthalpy using standard heats of formation. Now this is just another method that we can use to solve the heat change of an overall reaction, just like we did with Hess's law or with stoichiometry in two of our previous videos. So what we're going to be doing here is actually using a formula that's on the formula chart, along with some values that they give us for these heat of formations. So first off, let's talk about a definition for a heat of formation. Its symbol is delta H with a little subscript of F, and it is defined as the change in enthalpy or heat that accompanies the formation of 1 mole of a compound from its individual or constituent elements, all in their standard state at SATP conditions. Remember, SATP is kind of like room conditions, standard ambient temperature and pressure. That's 1 atmosphere and 25 degrees Celsius. By the way, because we're at SATP conditions, that's the reason why you see that little extra exponent 0 up here with our heat of formation symbol to represent those standard ambient temperature and pressure conditions. So to give us a better idea of exactly what a heat of formation value is, let's look at some actual values. So if you kind of look a little further down here, they give us the heat of formation value of sucrose, carbon dioxide, and of water. So let's talk about the sucrose for a minute. If I wanted to think about the elements that I'm putting together to get sucrose, well, I would need to put together carbon, hydrogen, and oxygen. And if I think about what state that those would be at room conditions, I know that carbon would be a solid at room conditions, hydrogen would be a diatomic at room conditions and a gas, and oxygen would also be a diatomic gas at room conditions. And if I only want to form 1 mole of that sucrose, I would want to put together 12 of the carbons, 11 of the diatomic hydrogens, and 5.5 of the diatomic oxygens in order to get that 1 mole of sucrose. So the heat change associated with this particular process, this reaction, is a negative 2,226 kilojoules per mole. The same idea goes for carbon dioxide and water. To form 1 mole of carbon dioxide as a gas from 1 mole of carbon as a solid, room conditions, and 1 mole of diatomic oxygen as a gas at room conditions, that would release 393.5 kilojoules for every 1 mole of the carbon dioxide. And same thing here goes for water. To form 1 mole of that water as a gas, I would need to react together 1 mole of H2 as a gas, a 1/2 mole of O2 as a gas, as those are room conditions, and I'm forming 1 mole of that water that would release 242 kilojoules per every 1 mole of the water that I'm forming. Now, a couple tidbits here that I want to mention about heat of formation values. First off, they do typically end up being negative, and the reason why they're negative is because a lot of times I'm taking elements and simply bonding them together, and hopefully we remember that we free energy when we form bonds. Now, on occasion, if I have to break apart some diatomics before I form that product and the heat change allows it to end up being positive, but that's very uncommon. Most of the time our heat of formation values are negative because those formation processes are exothermic. Something else I have to watch out for are the states. While this is the heat of formation to form water as a gas, there would be a different heat of formation to form water as a liquid. Why? Because there's a heat change associated with going between a gas state and a liquid state. And so we would see that reflected in that heat of formation value. So keep that in mind. We want to be very careful on those states. Now, one other thing about heat of formation. If I am trying to report the heat of formation of a singular element in its standard state, that heat of formation would be 0. I wouldn't see it reported on our chart. The reason why is because the element is naturally in those conditions at its standard state. There's no energy needed to form it because it's already as that element. So kind of a weird circumstance there, and we actually utilize that when we do our calculations to our advantage. Now, if I'm given all of these heats of formation value, we can find the heat of a reaction by using this equation right here, which is on your formula chart. You notice that the delta H of the overall process is the sum of the heats of formation of all of the products added together, minus the sum of the heat of formation of all the reactants all added together. Now, we have to be really careful with coefficients. I say that because these heats of formation values are specific for forming 1 mole of that compound. Forming 1 mole of sucrose releases this much heat, or forming 1 mole of carbon dioxide releases this much heat. But if in my reaction I have 2 moles or 3 moles or 4 moles, then I'm going to have to multiply that heat of formation by that coefficient. So we are going to have to utilize coefficients as we do this. So let's go ahead and see how we would do this in an actual problem. So most of the time, you're not required to write all of these reactions like we see here. We are just simply going to calculate for the reaction either that we're given or calculate for the reaction that they tell me they're right. Here, they want us to write this balanced reaction for the combustion of sucrose, and then we're going to calculate that reaction's value overall. So to start us off here with the combustion, hopefully remember that combustions are plus O2 yields CO2 and H2O. And so that was give us an equation that looks something like so. Now I did go ahead and put states, and if you notice on the water, I went ahead and put a gas. Since the heat of formation value they gave me was for a gas, I can assume that that was probably what I was forming in this particular reaction here. Now you notice I did something kind of extra. You're like, Marusik, I think I know which side is the reactant side and which side is the product side. I know, but I always go ahead and label those two as I do these types of problems, because I got to be really careful on that equation up above. That equation up above is products minus reactants, meaning I've got to address this product side first and then subtract the reactant side. So I like to label those just to kind of help remind me that I need to be careful of which side I'm dealing with first. So let's talk about the actual calculation that I would do. So let me go ahead and throw it up here. So first what I did is I wrote my equation of the fact that I'm calculating the delta H of this overall process by doing products minus reactants. And so I dealt with the product side first over here. So the first product was CO2. I see that I have 12 moles of that, but I know to form every 1 mole of CO2 would be a negative 393.5 energy change. And so what I did is I took that 12 and multiplied it by that negative 393.5. Now I'm going to sum that. I'm going to add it to my second product over here. My second product is the water. I have 11 moles of that, and I see for every 1 mole that would release 242 kilojoules. And so I'm going to do 11 times that negative 242. Now that's the last of the products, so I kind of close those off, and then I put my minus sign for subtracting the reactants. Now the first reactant was the sucrose over here. I only had 1 mole of the sucrose, and I see to form 1 mole of the sucrose would be a negative 2,226 kilojoules. So I put that math down. And then I'm like, well, wait a minute, my table doesn't give me a value for O2. But if you look at O2, it's an element by itself, and it's in its standard state. And so the reason why they didn't give it to me in this table up here is because it is going to have a heat of formation value of 0. It is an element in its natural room condition, standard ambient temperature and pressure state. And so that's why I put that 0 in there. Now, once I see it's 0, do I really have to include this? Like, would this really affect my math? And the answer to that is no. Like, honestly, if you left that out, it wouldn't be the end of the world, because we understand that by leaving it out, that value would end up being 0. So then I just simply plug in my math. And when I plug in this math, that gets a value of a negative 5,158 kilojoules per mole of the reaction, which means I know now that it's exothermic. I know for every one of these reactions, I'm going to release this much heat from the system into the surroundings. So then it asks me some other questions up above. It asks, is the reaction endo or exothermic? Well, as I just said, because that came out negative, I know it's exothermic. I also know what a potential energy diagram would look like. I know it's going to start high and end low, and that the amount of heat lost would be that negative 5,158 kilojoules. Now, some of you might be thinking, hey, when you wrote all those reactions up there, this kind of could almost be considered like a Hess's law problem. Like, could I have done this with Hess's law? Actually, you could have. Now, that would require you to write all these, but look at the math we ended up doing. Notice I needed sucrose on the reactant side. Well, this equation had it on the product side, so I need to flip that, right? So I would need to flip that sign. Well, look, I did a negative of that negative number, so that in essence flipped the sign on it, right? Well, look at the CO2. It's on the correct side, but I need 12 of it for this to work out. And so I needed to multiply that heat change by 12, which is what I did here. Same thing goes for the water. I needed 11 of it on the product side. It's already on the product side, but that means I'm going to need to multiply it by 11, and that in essence is what I did here. So you could very easily do this as a Hess's law problem. That would just require you to write all of these heat of formation reactions, which is kind of the pain in the butt if you don't have to do it. And we're given this lovely equation here to use. So I say, hey, let's just use the equation and save ourselves the time of having to write all these. But in essence, what we're doing here is an application of Hess's law, even though at first glance it doesn't look like that. All right, let's go ahead and look at the two that are on the next page. So the first one says that, hey, nitroglycerin is a powerful explosive that forms 4 different gases when detonated. So the first thing that I would do here is just like I did on my previous problem, I would label my reactant side and I would label my product side. And I see that they've given me here some heat of formation values, but I also notice that they don't give me the heat of formation of everything. And I'm like, okay, well, I see the nitroglycerin, I see the carbon dioxide, I see the water. Where's the value for the N2 and the O2? Like, I don't see those values. But keep in mind, those are elements by themselves. And if I look at their state, I notice that nitrogen here is a gas and oxygen is also a gas. I know that those are their states at room conditions. And so what that means is that both of those would have heat of formation values of 0. And so therefore, I don't need to include those in our math. So here's what I want you to do. I want you to go ahead and pause the video and take just a moment and see if you can solve A. See if you can use the values in the table to calculate the delta H of the reaction. So go ahead, pause it and try it out. All right, did you pause it? Did you try it out? I'm going to hope that you did. Let's go ahead and talk about what the answer would be. So here's what I got for both my work and my answer. So again, I did my products first minus my reactant. I made sure to take these heat changes that were originally per mole and multiply them by the number of moles that I had in my reaction. Okay, that got a value of a negative 5,686 kilojoules per mole of the reaction. So now think about all the things I know. This came out to be negative, it's exothermic. I know that heat is going to be released from the system to the surroundings. I know that this would feel hot to the touch, which makes sense because, hello, it's an explosion, right? I know all kinds of things about it. But think about what else I could do with this reaction now. Now that I have the amount of heat in kilojoules per 1 mole of the reaction, I could even use this value, say, in a stoichiometry problem. So notice on part B up here, it says find the enthalpy change when 10 grams of nitroglycerin is detonated. So this amount of heat is for 1 mole of the reaction. Well, look at 1 mole of the reaction. It has 4 moles of nitroglycerin in it. So this heat is for 4 moles of nitroglycerin, but I want the heat change for 10 grams of nitroglycerin. So that means I'm going to be doing a stoichiometry setup. Now I'm going to go ahead and put my work up here, but this is exactly what we did in one of our previous videos. I would say, hey, that 10 grams of nitroglycerin, so that's this long compound here, let me go ahead and convert that into moles. So I found the molar mass of this compound and said, hey, that's for every 1 mole of nitroglycerin. So then I'm going to do a mole to kilojoule situation. Well, I know that this number of kilojoules here is for every 1 mole of the reaction. And I see for every 1 mole of this reaction that I have specifically 4 moles of nitroglycerin in it. So that means I can set an equality up that for every 4 moles of nitroglycerin, that would release that 5,686 kilojoules. And so therefore, I could figure out that for every 10 grams of nitroglycerin, reaction, I would release 62.6 kilojoules. Now, let me go ahead and pause here and talk about sig figs for just a moment, because I know some of you are looking at some of these numbers and being like, okay, how is she deciding where to round? First off, on our delta H up here, when we're doing those heats of formation, usually I round based on adding and subtracting rules, because that's what I'm doing here. So remember, adding and subtracting rules utilize the least number of places past the decimal. I see that I have two numbers that have no places past the decimal, while I have another one that has one place. So I would report my answer to no places past the decimal. However, when I do my stoich problem here, remember, anytime I do stoichiometry, I base my sig figs based on my starting number of that stoich calculation, which here had 3 sig figs. Constants and conversions don't count, and so therefore I showed 3 significant figures in my answer. All right, we got one more problem down here. This one's a little bit different. If we start reading through this problem, we notice that what they're asking us here is actually to solve the standard heat of formation of cyclohexane, and which means they're actually asking us here to solve what data piece goes in this table for this compound of C6H12. So if we look at the information that they give us in the problem, they actually give us the standard enthalpy of combustion of cyclohexane, which is the heat released if I burn 1 mole of it, and they tell us that that value is negative 3,924 kilojoules. Well, convenient for us, this reaction is burning 1 mole of cyclohexane. So what that means is that this is also the delta H of this particular reaction, because this reaction is the combustion of 1 mole of that compound. So what I need to do is basically plug everything into my heat of formation equation, just like we've done before, except this time I'm going to know the heat of reaction, and I'm going to be looking for one of the heats of formation. And so what we're going to do is, as we plug everything in, we'll put in X for the C6H12's heat of formation and solve it using algebra. Now, the first thing I'm going to do is, just like I always do, I'm going to label my reactants and my products, because of course we're going to use that products minus reactants equation. And so I just want to be very clear about what should go on each side. I also noticed that over here in the table, they don't give me a heat of formation for oxygen, but of course oxygen, being an element by itself in its standard state, would have a heat of formation of 0. And so therefore I'm not really going to have to worry about it in my work. I'm going to just exclude it out of my equation. So what I'm going to do is I'm going to plug in everything I know, except now I'm going to plug in this value, that negative 3,924, for the delta H of the overall reaction. And when I plug everything in, I end up with something that looks like this. So again, it's that same heat of formation equation. This time though, I know the total. I have my products here, the CO2, 6 of it, times the 393.5 negative from the table. I also have water here, these 6 waters times negative 286. Now I did need to be careful. I noticed they gave me 2 different values for water's heat of formation, so I had to be careful about which state I have. We had a liquid, so I wanted to use the negative 286. The H2O as a gas, you notice, is a little bit less energy getting released, and that would be because we're utilizing some of the energy to break forces when we go from a liquid to a gas. And so when I have it in the gaseous state, that's going to release less energy. And then I have minus my reactants. Now I didn't include the oxygen, but I did put 1 for the mole of the C6H12 times the unknown value of X. And so X is going to be kind of our goal on what we're trying to solve here. So on solving this algebra, what I would do is I would add up all of these numbers here that I have in pink, multiply and add them together in order to get what that value, that answer should be. And whatever that answer is, that would have minus X equaling the negative 3,924. And so in order to get X by itself, what I would first do is subtract the value for the pink numbers from the other side. And then I would have to flip the sign, because obviously I don't want to solve for negative X. I would want to solve for positive X. So you're just using using simple algebra in order to finish solving this problem. And what that ends up getting for the value of X is that equals a negative 153. That would be in terms of kilojoules. And because it's the heat of formation for this C6H12, I put per mole of the C6H12. And again, this is the heat of formation value that would have gone in a table like this for that cyclohexane. Now, it asks us to do something else here. It says to write the reaction for the formation of cyclohexane that would go along with this value here. So basically, what is the heat of formation equation in order to make C6H12 as a liquid? And so I would want to think about, well, what elements would I need to put together in their standard state in order to form 1 mole of this C6H12? Well, hopefully we can see here that I would want to put together carbon and hydrogen. I know carbon at room conditions is a solid. I know hydrogen at room conditions is both diatomic and a gas. And so in order to form 1 mole of C6H12, I would need 6 of those carbons to make this C6. And in order to make H12, I would need 6 of the diatomic hydrogens. So this is the heat of formation equation that goes along with this value. This reaction here would release a negative 153 kilojoules for every mole of C6H12 that I'm forming. All right, I hope you're feeling good about heats of formation and using this idea of products minus reactants. If you have any questions or need any help, please feel free to email me. Bye, guys.